Today we are meeting on National Science Day. On this day, that is 20th February, in the year 1928, Raman made official declaration of his demonstration of Raman effect. I welcome you on behalf of Vijnana Bharati. Chandrasekhar Venkat Raman, his name, he was awarded Bharat Ratna. Before that, he was awarded Sir name by British government. So earlier he was called as Sir C.V. Raman, but we will call him as Bharat Ratna C.V. Raman. Let us talk a little about his family background. His father, Ramanathan Chandrasekhar Iyer, was a physics and mathematics teacher. His brother, Chandrasekhar Subramaniam Iyer, was Class 1 gazetted officer in Indian Finance Services. His wife, Lokasundari Ammal, was social worker. His popular nephew, S. Chandrasekhar, was astrophysicist. He was awarded Nobel Prize in Physics on his discovery of what is called as Chandrasekhar limit, which is 1.4 times mass of the sun, that is the maximum mass of a stable white dwarf. If the mass of the white dwarf becomes larger than that, it becomes neutron star or the black hole. His son, Radhakrishna, he was also a good astrophysicist. He was good in radio astrophysics. He was director of Raman Research Institute from 1972 to 1994. One interesting thing about his son and his nephew, S. Chandrasekhar, was both of them were astrophysicists. Earlier, Raman was not interested in astrophysics. Instead of astrophysics, he was insisting on his son and nephew to work on nuclear physics because that was the very important field in those days. But both of them refused and they kept on working in astrophysics. His another nephew, that is son of his sister, S. Ramashishan, was director of IISc from 1981 to 1984. There were some important turns in life of Sir C.V. Raman. He was born on 8th November 1888. At the age of 11, he passed matriculation examination in 1899. He passed BA in physics in 1904. And after his BA examination, all intelligent students in those days, they were going to UK for further studies and to prepare for ICS examination. So the family of Raman also insisted that he should go to UK for further studies and prepare for ICS examination. But civil surgeon at that time refused to give him the fitness certificate. He said that uh, Raman is not fit to go to UK. And that was the first turning point in his life. Later on, C.V. Raman on one occasion said that he is very much thankful to that civil surgeon who didn't allow him to go to UK for further studies because that gave him chance to study physics in India itself and do the physics research in India. He passed MA examination with physics and maths in 1907. An interesting thing is that while he was studying in the college, he published two research papers in international journals. Those were first research papers from a student in those days from his college. Those papers were based on a new method to determine surface tension, and another paper was diffraction pattern of light for oblique incidence. Here I would like to tell you the out-of-box thinking ability of Sir C.V. Raman. He was thinking on studying of diffraction pattern of light from a single slit and double slit. Normally, whenever we study diffraction pattern, we do normal incidence. That is, the light is incident on the slit in a direction perpendicular to the slit. And here the angle of incidence is 0 degrees. But then Raman started thinking what will happen if the light doesn't fall normally on the slit? Because normal incidence is a very special case whereas the oblique incidence is a general case. So he started studying the diffraction pattern for different angles of incidence and the symmetry and asymmetry in the diffraction patterns. And this paper was very important, and Lord Rayleigh liked that paper much. In 1907, after passing MA, he joined Indian Finance Services as Class 1 Gazetted Officer with the first rank in the examination, and he was appointed as Assistant Accountant General in the Finance Services. That was a very highly reputed post. On 2nd June 1907, he married to Lokasundari. It was intersect marriage, first of its kind in city, and because of that, that marriage was very popular in those days. While traveling to his office from his home, in the month of August in 1907, he saw a board of IACS, that is Indian Academy for Cultivation of Sciences. It was established by Mahendralal Sarkar. And after his death in 1904, his son Amrutlal Sarkar took the office of IACS. He was in fact waiting for good people who will do research work as per the dream of Mahendra Sarkar. So he welcomed C.V. Raman to work in the IACS. In those days, from 1907 to 1917, till he was working in the Indian Finance Department, his schedule was very tight. He used to wake up early in the morning, and at 5:30 a.m., he used to go to IACS. From 5:30 a.m. to 9:30, for 4 hours, he used to work in IACS on different physics experiments and different physics theories. And he used to go to home and come back to his office at 10 a.m. From 10 to 5 p.m., he used to work in government office. At 5:30, he used to go back to IACS and work there till 10 p.m. So approximately 9 to 10 hours in IACS and 8 hours in government office. He was a very popular finance officer then. He was so intelligent that his seniors thought that one day he will become finance secretary and then he will become finance minister for India. So he was very good in finance. In that period of 10 years, he published many papers in the very reputed journals like Nature, Physical Review Letters, and Philosophical Magazine. These are very reputed journals. In fact, the research workers and professors like me, they feel themselves very lucky even if they publish one single paper in Nature. But while he was working in government office, he published many papers in Nature and Physical Review Letters. At that time, he was getting a salary of 1400 rupees. In 1917, the Vice Chancellor of Calcutta University, Ashutosh Mukherjee, invited him to join as Polit Professor in the university. But the salary he offered was just rupees 600. See, leaving such a great post of great honor, social repute, the government job, it was difficult. The salary was much less, but then the passion of C.V. Raman for the experimental research in physics, made him resign from the government job, and he joined as Polit Professor in 1917. And then he started working as a full-time professor and research worker. There was another turning point in his life in the year 1921. When he was traveling back to India from England, he was continuously thinking of blue color of seawater. See, the blue color of sky was very well explained by Lord Rayleigh based on the theory of scattering. We all know that sunlight is white. It has many components, it has many colors from blue to red, and the scattering of light depends on the wavelength of the light. Smaller the wavelength, larger is the scattering. It is proportional to the fourth power of wavelength. Blue color having smallest wavelength in the visible spectrum, it gets scattered most. If the wavelength is doubled, the scattering becomes 16 times larger. So whenever light of the sun enters the atmosphere of the earth, it gets scattered from the molecules of air in the earth's atmosphere, and the blue color gets scattered most, and rest of the colors enter into the atmosphere of the earth. So at that level of around 16 kilometers from the surface of the earth, where the atmosphere starts, the entire blue light is scattered and we see the sky as blue. Now, Rayleigh was saying something about the blue color of the sea, which I will explain later on, but he proved that Raleigh's explanation for sea color of the seawater was wrong. In 1922, Raman predicted that scattering of light can be explained only if quantum nature of light is assumed to be true. This was a very important statement made by C.V. Raman. In 1923, Semkale gave the theoretical prediction of Raman effect. In 1924, he was made Fellow of Royal Society. And in the honor of that, a party was organized in Calcutta University, where the Vice Chancellor Asutosh Mukherjee said, Raman, now you're Fellow of Royal Society. Now what is next? He immediately said, Sir, I will bring Nobel Prize to India in next 5 years. And you will see on 28th February 1928, he declared the experimental verification of Raman effect. He was very confident that he will get Nobel Prize in 1928. So he booked his ticket for going to the ceremony, but 1928 and 29 he didn't get Nobel Prize. In 1930 he got the Nobel Prize. So see the confidence in Raman's words. 1924 he says in next 5 years he will bring Nobel Prize for India. 1928 he discovered the effect and got the Nobel Prize. From 1933 to 1948 he worked in IISc and then he established Raman Research Institute. While talking about C.V. Raman, it is always important that we should speak about the work of C.V. Raman on musical instruments. C.V. Raman developed lots of theories on the working of musical instruments. The musical instruments basically of two types he studied, the membrane instruments and the string instruments. And he developed mathematical derivations on the frequencies, pitch, and quality of sound emitted by these instruments. Here in the picture, you will see the Western membrane instruments. We can call them as drums. You will see that these are single stretched membranes. And these instruments do not produce very good quality sound. In fact, that's a very bad sound as far as quality of the sound is concerned. You see the Indian musical instruments of membrane type, tabla, dagga, and so on. In the picture, you will see that there is ink patch. There are different areas on the membrane. These areas are having different thicknesses and different densities. Due to these differential thicknesses and densities, the quality of sound produced by these instruments is very good. They are rich in harmonics and overtones, and therefore, if you hear the Indian membrane instruments, you can really correlate with the song that is being played. The quality of sound is excellent, and Raman theoretically proved that this differential density variations and thickness variations are useful in the production of good quality of sound. And you will see that these instruments are thousands of years before, they were developed thousands of years before. So our people were knowing all the mathematics and theory behind these instruments. Here you see a violin, which is not Indian instrument, it is a Western instrument. And you will see the strings and the tension applied to the string and the knife edge, that is the bridge. If you see the Indian string instruments, which are sitar, sarangi, veena, tanpura, etc., you will see lots of ways of varying the tensions in these strings, you will see the different shapes of bridges, that is knife edges, used in these things, in these instruments. The simple shape and sharpness of the bridge also changes the quality of sound. He showed that the sharp knife edge in the Western instruments like violin, they do not produce good quality of sound. So if you use different types of knife edges, that simple change in the knife edge produces a very good quality of sound. And he developed mathematical equations on that, showing the quality of sound. And he mathematically proved that the quality of sound in the Indian instruments is much, much better than the Western instruments, again because of the higher harmonics and overtones present. Here you will see a picture of Gol Ghumad, which is a whispering gallery. There were many whispering galleries in the Eastern countries, particularly in churches. What is that whispering gallery? That is a dome-shaped building. You whisper in one corner of that building. That whisper is very clearly heard in the another corner, which may be around 50 or 100 meters away from that place from where it is whispered. It was earlier thought to be a miracle of the building like church, and it was assigned some religious reason. But Raman said there is nothing religious in that. There is complete physics, and he explained this on the basis of reflection of sound. You speak at one end, you will see that you will hear the whisper at the another end. It is because of the multiple reflections. The sound travels along the circumference of those buildings. So wherever you put your ear, you will see the whisper, and maybe you will hear multiple reflections also. So this is the very good explanation given by Raman in the whispering gallery phenomenon, and he showed that many buildings in India, they show this phenomenon. It is not a unique phenomenon in the Western buildings. It is a phenomenon which is observed in all types of dome-shaped buildings, and it is present in many temples and buildings in India. Now coming to Raman spectroscopy, because Raman effect is a Raman spectroscopy. So we must know what is a spectrum. Spectrum is, in a simple, very simple word, it is a band or set of colors that is visualized by our eye. These colors, if you observe by naked eye, they may be bands of colors. If you observe them with the help of instrument called a spectrometer, it will be, these will be sharp lines, colored lines, or the spectrum, band spectrum. The spectra, if you see the sunlight, it consists of many colors. Ultraviolet, which are not visible, which are having small wavelengths. Visible light, which is in the range of 400 to 700 nanometer wavelength. And if the wavelength is beyond that, it is not visible again to human eye. It is infrared region. So even solar light, which appears to us as a white light, it consists of many wavelengths. Visible wavelengths are in the range of 400 to 700 nanometers. The spectra are of different types: absorption and emission spectra. What is this? If you heat a certain substance, it emits light. Suppose today you take an iron wire and keep it on the burner. After some time, you will see that its color changes from red to white. So in fact, this is emission spectrum of that substance. Even the burner you see is of different colors. Sometimes it is blue, sometimes it is yellow. So that is a spectrum. So what is emission spectrum? Whenever a substance is heated, it gives out radiation in the form of light of different wavelengths. Visible light that we can only see. Of course, it emits lights or electromagnetic radiations of different wavelengths which are not visible also. Whatever we see is only small part of that spectrum. So here you will see sodium emission spectrum, wherein you can see some bright lines of light of different colors, and these are separated by complete dark regions. So it means that sodium emits certain wavelengths of light only. Now, what is absorption spectrum then? There is a principle. Whenever a substance is hot, it emits certain wavelengths. And whenever it is cold, it absorbs those wavelengths only. So now suppose you take sodium flame. What do you mean by sodium flame? In the gas burner, you just burn sodium. So you take a cloth or a wire gauze, dip it in sodium chloride solution and hold it in the burner. You will see the yellow flame of sodium. So it emits mostly yellow color. Now, take a bulb, maybe a 1000-watt bulb. It will emit white light. The temperature of that filament of the 1000-watt bulb is very high, of the order of 5000 degrees centigrade. Now, this light, when it falls on the sodium flame, you will see that certain wavelengths are absorbed. That means light waves corresponding to certain wavelengths are absorbed by that sodium flame. And whenever you see the entire spectrum of that white light emitted by the bulb, you will see black lines in some places, exactly complementary to the emission spectrum. What that black line indicates? Black line indicates the absence of light. That means the light of that wavelength is completely absorbed. So on the scale, if you see 500 nanometer, when sodium is hot, it emits a wave of 500 nanometer wavelength. When it is cold, it absorbs a wave of 500 nanometer wavelength. So here you will see the absorption and emission spectra of sodium, nitrogen, hydrogen, oxygen, etc. And again, you will see that whenever there is a black portion in absorption spectrum, there is corresponding colored spectrum line in the emission spectrum. Now, spectra are also classified differently. One is called as line spectrum, particularly when the elements or atoms, pure atoms are excited, that is, they are given energy in the form of heat, like sodium, hydrogen, calcium, mercury shown in this slide. You will see the lights of different wavelengths emitted by them. These lines correspond to the light emitted. So sodium, if you consider, you will see 2 plus 2 plus 2 plus 1, 7 different wavelengths emitted. These are broad. There are many small wavelengths also. There are many small lines also. Hydrogen, you will see prominent 4 lines. Calcium, you will see more lines. So whenever an atom of an element is excited, you will see it will emit light of different wavelengths. Specific, very sharp wavelengths. What is the phenomenon? The phenomenon is very simple. Whenever you give energy to the atom, that energy is absorbed by electron. That electron goes into higher energy orbit and the atom becomes unstable. That electron becomes unstable. The tendency of everything in the nature is to go to the stable state. So that electron tries to go to the stable state, that means its lower energy state, by giving out energy, and it becomes stable. This energy is radiated in the form of electromagnetic wave. And when it is radiated in the wavelength region 4000 angstrom units to 7000 angstrom units, we can see it. So when sodium is heated, the electrons go to higher energy levels. When they come back to their stable states, they emit lights of around 5000 angstrom unit, 5700 angstrom unit, 6000 angstrom units, and so on. So this is the basic principle by which the elements or atoms radiate energy in the form of monochromatic wavelengths. Now, there is another form, another type of spectrum, which is a band spectrum. Now, what happens is when you consider molecules, the molecules are complex structures. The molecules are having different types of motions, like vibrational motions, rotational motions. What do you mean by rotational motion? The atoms in the molecule are rotating about some common center. Of course, the electrons are also revolving. So the molecular spectra are of different types: electronic spectra, vibrational spectra, rotational spectra. So the molecules are having very many energy levels. And when you give energy to such a molecule, the energy levels change because that energy is absorbed. And the molecule wants to go to the stable state because of its natural tendency. So all these different energy levels, they radiate energy and come to original state. And therefore, whenever a molecule comes to original state, lots of waves of lots of frequencies and wavelengths are emitted. And therefore, instead of observing sharp lines, you observe a band. So this is about spectra. Now, Raman effect is based on scattering of light. So let us see what is scattering of light. You consider incident light, it is a beam of photons. When a beam of photons is incident on an atom or a molecule, what happens is it is absorbed and they are re-emitted in different directions. That means these photons are diverted by the molecules. Some in one direction, some in other direction, some in other directions. So the beam of incident photons is now said to be scattered. This incident light ray is said to be scattered in different directions. This phenomenon is called as scattering of light. Now, coming to what I said earlier, Rayleigh gave the explanation of blue color of the sky. In the graph, you will see that percentage scattering of direct sunlight. You will see that the blue color is scattered most and all other colors are scattered much less than the blue color. And therefore, in the atmosphere, the sun rays, when they enter into the atmosphere, they hit the molecules in the atmosphere and they are scattered. And you will see that the blue color is scattered most, all other rays are scattered least, and they reach to the Earth's surface. Therefore, you will see the sky color as a blue. This explanation was given by Lord Rayleigh, who was a Nobel Prize winner in physics. Now, coming to, as I said, blue color of the sea. Rayleigh said that the blue color of the sea is simply the reflection of blue sky. But Raman was not confirmed. He didn't agree with Lord Rayleigh. See, what happens is when a great scientist, Nobel Prize winner like Lord Rayleigh says that the blue color of the seawater is because of the reflection of the blue sky, then all simply agree with Lord Rayleigh because Lord Rayleigh is proven to be a great scientist. But Raman didn't accept this. He said that it is not because of the reflection. For that purpose, he studied what is the absorption of sunlight in the seawater. He saw that the blue color is absorbed till the depth of around 300 meters in the sea. All other colors are absorbed in the depths less than that. So the blue color is there in almost all layers of the water of the sea. Now, what happens is, again, that blue color, its wavelength is comparable to the molecular size of the seawater, and therefore, being a smallest wavelength and having the size comparable to the molecules of the water, it gets scattered most. And therefore, the blue color of the sea is because of the scattering of the blue light due to the water molecules of the sea. It is not because of the reflection. Now, why Why it is not because of the reflection? Raman was very good experimentalist. He used to carry many instruments in his pockets. So when he was traveling from England to India, he was having a Nichols prism in his pocket. What is that Nichols prism? That Nichols prism is used to detect polarized light. What is polarized light? Light is electromagnetic wave. In the light wave, when the light wave is traveling, the electric field and magnetic fields are traveling in a mutually perpendicular direction like this. And these electric and magnetic fields are oscillating in different planes like this. This is called as unpolarized light. So in unpolarized light, the electric and magnetic fields are vibrating in many planes. And in the polarized light, the electric and magnetic fields are vibrating in only one plane. One plane of magnetic field and one plane of electric field. So polarized light, it has got only one plane of vibrations of EM field. Now when axis of the Nichols prism is perpendicular to the plane of polarization, then that light doesn't pass to the Nichols prism. And on the other side of the Nichols prism, you see complete darkness. So the Nichols prism is used to check whether a light is polarized or not. So what Raman did, Raman was knowing one theory that whenever light is reflected from a surface, it gets polarized. That means it gets completely polarized for some angle of incidence. So if the axis of the Nichols prism is held at that angle, then the light coming from the Nichols prism will be totally stopped. So he took the Nichols prism and he rotated that. For different orientations, he saw the intensity of light coming out of the Nichols prism and he saw that the intensity of light doesn't stop anywhere. That means he never saw complete darkness on the other side of the Nichols prism. It means that the light reflected from the sun surface is not plane polarized. That means it is not a reflection of the sky. It is simply the light coming out from the water surface. So this is how he proved that Lord Rayleigh was wrong. Now coming to the real Raman effect, which is optical analogous of Compton effect. What is Compton effect? It was also a very important phenomenon in physics. Compton got Nobel Prize for this. See what experiment he was doing. He took X-rays and allowed those X-rays to fall on the atoms. When the X-rays scattered by electrons in the atom, what happens is, number one, the direction of the X-ray is changed. And number two, the wavelength and frequency and the energy of the X-ray photon is changed. What is the theoretical reason for that? Whenever the X-ray photon is incident on the atom, see, photon is having some frequency, say nu. So its energy is h nu, where h is Planck's constant. So when photon with energy h nu falls on the atom, some of its energy is taken away by the atom, electron in the atom. Electron goes to excited state. Therefore, the energy of the incident photon becomes less. So when it comes out of the atom, it comes with the lesser energy, that means lesser frequency, that means with the larger wavelength. If you see the diagram, you will see that the wavelength of incident photon is smaller and wavelength of scattered photon is larger. You see the long wave here. So it means that the wavelength, frequency, and energy of the photon is changed. This is Compton effect. Compton used X-rays in his experiment. Raman said X-rays are electromagnetic radiations. Visible light is also electromagnetic radiation. So whatever happens in Compton effect should happen with the visible light. So he said that whenever visible light is incident on the molecule like this, what should happen? There are three probabilities. One is that the energy of this incident photon is not absorbed and it is simply deviated from original direction. It is having same wavelength, same frequency, same energy. This phenomenon is called as Rayleigh scattering. Can you see the cursor here moving? Now, one thing may happen that when this photon of light is incident on the atom, some of the energy of this photon is absorbed by the atom or molecule, and remaining energy is given out, and the direction of the light is changed. So you will see that the light that is scattered, that is coming out now, is having less energy, less frequency, and therefore larger wavelength. So lambda scattered is greater than lambda laser or original incident wavelength. There is third possibility. The molecule may be in the excited state itself. And therefore, when the incident wave hits that molecule, the molecule will give some part of its energy to the photon, and then that photon will emerge out of the molecule with larger energy, larger frequency, and therefore smaller wavelength. That is called as anti-Stokes-Raman scattering, where the scattered wavelength is less than the original incident wavelength. So in the Raman spectrum, Raman said that as Semkel has theoretically predicted, when the light is incident on a liquid or gas, three things should happen. The light with same frequency should come out with the change in direction, that is called as Rayleigh scattering. The light with small frequency and small energy, that is larger wavelength, will come out, that is called as Stokes scattering. And the light waves with larger energy, larger frequency, and smaller wavelength will come out, that is called as anti-Stokes-Raman scattering. I have explained this theory of Compton effect and Raman earlier now. Compton effect was discovered in 1923 and he was awarded Nobel Prize in 1927. As I said, Raman thought that X-rays are electromagnetic radiations. Visible light is also electromagnetic radiation. So whatever happens in X-rays should happen in visible light also, and that is what he expected. Now he performed lots of experiments from 1921 to 1928. Almost 7 years he performed lots of experiments. Around more than 500 liquids and gases were studied. Their spectra were studied and the observations were made. Here you will see the Raman effect in oxygen and nitrogen. Okay. Here the central line, which is very bright, is incident light. And on both sides, that is on smaller wavelength side and longer wavelength side, you will see the lines of different intensities, different frequencies, and different wavelengths. You will see that on larger frequency side, that is smaller wavelength side, the lines are having less intensity. The lines are less in number, they are less intense. But you will clearly see all the three types: original wavelength, smaller wavelength, and larger wavelength, as predicted by Semkel and observed by Raman. This was first observed by Raman. No other scientist in the world could observe this. In fact, the instrumentation available with Raman was very crude. He was not having very sophisticated instruments and spectrometers. Till then, he observed this. Initially, they thought that these lines, particularly on these sides, that is on smaller wavelength side, they are due to the impurities present in the liquids. But then they took the pure liquid, 99.99% pure liquid, still then they observed the same effect. These are Raman lines in benzene, carbon tetrachloride, acetylene, calcite crystals, diamond. So different gases, liquids, and solids. You will again see intense incident line and then weak lines on both sides. This is a spectrometer, rough sketch of the spectrometer used by Raman. In those days, obtaining a monochromatic light was very difficult. Now we have lasers which have very precise monochromatic light sources. In those days, the sources available were mercury lamp and the sunlight. The mercury lamp was difficult to use. You will see the water jackets around the tube because mercury lamp produces very large amount of heat. Okay. So the sample, then the pure darkness, darkroom you want, and then light should pass through it. It should pass through filters so that monochromatic light should be incident on the liquid, and then it should come out of the window slits, lenses to amplify, and then spectrometer to study. So this is schematic of Raman spectrometer. In those days, using mercury lamp was also very difficult because it requires a very large amount of electric power, which was not very easily available in the days. So when Raman used to work, he used to work on sunlight. See how it is difficult. You get limited hours only because sunlight is available for limited hours. Again, its intensity goes on changing. The sun goes on changing the position. So you have to use the instrument which is called as heliostat, which will rotate the instrument in such a way that the sunlight falls normally on the instrument. So that is a very difficult setup to perform, to use. And again, you get limited intensity, limited time, and many wavelengths are there in the sunlight. So you have to use many filters and get the correct monochromatic wave. The instrument that Raman used for his discovery was just 200 rupees cost. He used to go to Bhangar market to collect the components and connect them in the instrument. So it is really a jugaad made by Raman. 200 rupees instrument, he made the discovery which gave him Nobel Prize. Today we are spending crores of rupees and saying that we don't have facilities and we can't get the Nobel Prize. See the difference. See, this is the actual photograph of the spectrometer that is used by Raman. It was used in 1928. There's a photograph of Raman working on same instrument and explaining the Raman effect to its colleagues. This is the modern Raman spectrometer. You will see nothing. A very packed small instrument costing crores of rupees and giving you a Raman spectrum. Now, whenever you observe a certain phenomenon and you say that it is a new phenomenon, you have to prove that it is really a new phenomenon. It is not an old phenomenon. Earlier, there were different scattering phenomena. One, as I said, Rayleigh scattering, wherein the light waves come and fall on the molecules and they just get deviated. No change in frequency, no change in wavelength, no change in energy, just change in direction. But there was one phenomenon which was similar to Raman effect, which is called as fluorescence. What is fluorescence? There are some materials. Whenever light falls on those materials emit light of different wavelength or frequency. So now here you have similar phenomenon. Light falls on liquid and lights of different wavelengths and frequencies are emitted. So now you have to show how it is different from the fluorescence phenomenon that you have observed. Now in the fluorescence, it is observed that the scattered light was having always less frequency and larger wavelength than the incident one. So incident light is having certain wavelength and frequency. The scattered light will have frequency which is always less than the incident light. But in Raman, you see that the frequency, the light with larger frequency, that is smaller wavelength, was also observed. So one thing is clear that it is different from fluorescence. In fluorescence, you don't observe the light with larger frequency. You observe light with smaller frequency only because the incident photon light energy is taken away by the liquid, and the light with less energy, that is less frequency, is emitted. Now, in the Raman effect, it is observed that the lines with higher frequency are less in number and less in intensity. This is directly in confirmation with quantum statistical mechanics. First thing is Raman effect shows quantum nature of light, particle nature of light, photon nature of light. A photon is absorbed, not a ray is absorbed, not a wave is absorbed, a particle is absorbed. Now, quantum statistical mechanics, what it says, there is a certain thing called as density of states. The atoms and molecules are in different energy states. The molecules which are in high energy state are less in number. The molecules which are in less energy state are more in number. So, it means that excited molecules are less in number. These excited molecules are going to give the energy to the incident photon. So less number of photons will get energy. So less number of photons will be having higher energies. That means intensity of waves having higher energy or higher wavelength, frequency will be less because intensity is directly proportional to number of photons. So it again proves quantum statistical mechanics that the density of states with higher energy is less. Now, another difference between the fluorescence and the Raman lines is in the fluorescence, the frequencies of scattered lines are not dependent on incident frequency. They are dependent on scatterer only, which type of liquid you are using. But here in Raman effect, the frequencies of the scattered lines are dependent on scatterer as well as incident frequency. So you change the incident frequencies of scattered lights are changing. So scattered line frequency is a function of incident frequency, which is totally different, which is absent in fluorescence. So it shows that something other than fluorescence is observed. Again, in the Raman effect, in fact, not frequencies, the frequency shifts of Raman lines were dependent on scatterer. What do you mean by frequency shift? The incident frequency and the scattered frequency. The difference in those two frequencies is called as frequency shift. This frequency shift depends on scatterer. In the fluorescence, the frequency depends on scatterer. Here, frequency change depends on scatterer. So again, it shows that this is not fluorescence. Again, one more important thing, Raman lines are strongly polarized. So whenever light falls on the liquid and it gets scattered, the scattered light is highly polarized. Fluorescent light is not polarized. And Raman frequencies are either actual IR frequencies in the absorption spectrum of the scatterer or the difference in those frequencies. So all these 7 points show that this is a totally new phenomenon. See the logic that Raman has used. See the theory, see the thinking process of Raman to show how the observed effect, the observed phenomenon is a totally new phenomenon. It is not same as the old phenomenon. Because many times people just forget that it is a new phenomenon. They say that, yes, it is old phenomenon only. Raman was very out of box thinking person. He said that it is a new phenomenon. And therefore, he got Nobel Prize for that. Now you will see what you will say. What is the importance of this Raman effect? What is the application? In fact, Raman effect is applicable in our daily life. One thing is, Raman spectrum is unique for each compound. You take carbon tetrachloride, you take acetylene, acetylene, whatever compound you take, its Raman spectrum is different. So Raman spectrum is the signature of the molecule. So you can identify which molecule is present there, which substance is present there. Again, intensity of Raman lines depends on the concentration of the substance. So whenever I take carbon tetrachloride, I will identify that it is carbon tetrachloride by using Raman spectrum. And by considering the intensity of the Raman line, I can tell you what is the concentration of the substance. So it gives quantitative as well as qualitative analysis, chemical analysis of the material. Not only that, it gives information about the nature of chemical bonding, whether it is a single bond or double bond, triple bond, etc. So it gives you information about chemical structure. Not only atoms and molecules, it is used to determine the nuclear spin. So Raman effect is useful in nuclear physics also. It is used to study the isotopic constitution of the nucleus. So whether it is pure nucleus or isotope of that nucleus. Because the Raman spectrum is different for different materials, it is used for identification of impurities in the substances. What are the impurities present? What is the percentage of impurities present? Raman effect has got so many applications in biomedical field. It can identify the molecular changes in cells and tissues, and therefore it can detect various diseases. It can detect cancer even. So early cancer detection is very much possible because of the Raman effect. So it's good in all medical applications also. Because of all these characteristics of Raman effect, it is used in quality control, it is used in failure analysis of the materials, it is used in characterization of the materials, it is used in forensics. Nowadays, forensic laboratories are using Raman effect to detect many things. It is used in the drug detection also. So wherever you have packets, simply passing light through that and studying its Raman spectrum, instead of breaking that packet, you can detect what drug is present in the packet. So these are importance of Raman effects. Now coming to the last part, what are the awards and honors given to C.V. Raman? In 1912 and 13, when he was working in Indian Finance Services, that means he was part-time research worker, he was given Curzon Research Award and Woodburn Research Award. In 1928, he got award from Italy. In 1930, he was given Sir Award, knighthood by the British government. In 1930, he got Nobel Prize in Physics. He was the first Asian and first non-white to receive Nobel Prize in Science. He was Indian-born scientist working in India and got the Nobel Prize. Before him, Rabindranath Tagore got Nobel Prize in 1913, but it was for literature. In 1930, he received Hughes Medal of Royal Society. In 1941, he was awarded Franklin Medal. In 1950, he was offered a post of Vice President of India. But he refused because he wanted to remain as a scientist. See the dedication and passion towards science. Anyone will be very happy if he or she is awarded Vice President post. But he refused that. In 1954, he was awarded Bharat Ratna. Along with him, C. Rajagopalchari and Sarvapalli Radhakrishnan were also awarded Bharat Ratna. So, see the importance of C.V. Raman. He was awarded Bharat Ratna with those great personalities. In 1957, he was awarded Lenin Prize, Lenin Peace Prize. So this is a small thing that I wanted to talk to you about Bharat Ratna Sir C.V. Raman. Thank you for patiently listening. Thank you very much.